Okay, good afternoon, ladies and gentlemen. So we will begin our second lecture. Today's lecture will be given by Professor Akihiro Munemasa. Professor Akihiro Munemasa is a professor at Tohoku University, Japan. His research is in algebraic coding theory, association scheme, combinatorial design theory, spectral graph theory, and permutation groups. So from 1989 to 1991, he was with the Department of Mathematics, Osaka Kyoiku University, Japan, as a research associate. He moved to Kyushu University, Fukuoka in 1991 and was appointed there as an associate professor in 1994. And since 2003, he has been a professor of Graduate School of Information Science, Tohoku University, Sendai, Japan. Also, he had been one of the 4 editors-in-chief of Journal of Algebraic Combinatorics from 2000 to 2017, and then joined the team of editors-in-chief of the new journal Algebraic Combinatorics in 2018. So he has his bachelor degree in mathematics, also a master degree in mathematics at Sophia University, and then a PhD in mathematics at the Ohio State University, USA. So this is some of publication. There's also Dr. Gary Graves, the lecturer yesterday, also in his publication. Okay, Professor Munemasa, are you ready to start your lecture?
Okay.
Yes,
can you hear me?
Yes, of course.
So then,
okay, and your time will be 2 hours and 45 minutes, and we will separate with 3 parts, and then the last 15 minutes we will have the Q&A session. Also for participants, if you have any questions like yesterday, you may write your question during the talk at the chat Zoom. Okay, so please feel free to ask Professor at a chat box anytime. Okay, Professor Munemasa, maybe you can start to share your screen.
Okay.
Okay, thank you.
So, okay, can you see my slide?
Yes.
The first page?
Perfectly.
Okay.
Yes.
So at the bottom, you see lecture 1, and on the lower right corner, you have counter. This is first page out of 19 slides. So I have similar slides for lecture 2 and lecture 3. So this 3-hour lecture will be divided into 3 parts. Okay, so this lecture is about introduction to combinatorial design theory. So I heard that the most participants are undergraduate students, so I'll start with a very basic notation from mathematics.
Yes.
Okay, so I suppose you have never heard of what design theory is. So let me start with the notation I'm going to use. So if you're already familiar with the standard set theoretic notation, then you don't have to carefully listen to this part. But if you are not, then let me remind you the basic notation. So the Z will be the set of integers, and Q rational number, R real number, C complex number. But I don't use it very much. But what I'm going to use is the set theoretic notation, which samples are listed here. So, and for example, I will use this absolute value notation to denote the size of the set, the number of elements in the set. So the integers from 0 to 10, there are 11 elements, and that's how I express in this line. And power set, it is the set of all subsets of a given set A is denoted by 2 to the power A. and the set difference is A1 backslash A2, and then direct product set, this is denoted by times notation or cross notation. And if you make a direct product of the same set n copies, then it is denoted by power notation. Those are all standard, but there may be non-standard one in the last line, which is standard in combinatorics, but you may not be familiar with. So this binomial notation, which is usually read choose. So I would read A choose K. That is the binomial A choose K is not the binomial coefficient. It is a set of all subsets, because 2 to the power A is a power set of A. And so B being an element of 2 to the power A just means that B is a subset of A. And the condition is that the B has size K, where K is some non-negative integer. Of course, K exceeds the size of A, then this would be empty. So K is considered to be something between 0 and size of A. So in particular, if you count the number of elements in this set of subsets, then that is exactly the binomial coefficient, size of A choose K. So this is quite common in combinatorics, but not so common in outside combinatorics. Okay, so incidence structure, that is a more general concept than combinatorial design, consists of essentially a set family. Set family just means a subset of a power set of a set. So throughout this lecture, this curly P will be a set, and I will mainly interest in family of subsets of P, not all of them, but some subset of the power set. So such an object is called a set family, and the pair, this set family together with this underlying set P is called a combinatorial structure, or sometimes called incidence structure. I will mainly call incidence structure, and some people call point line geometry, etc. In a more restricted case, that is when some condition is imposed on this family B, it is called a linear space. Well, it's not to be confused with vector space, or a combinatorial design, which I will define shortly. So this concept, incidence structure, is a quite general concept. And the term point line geometry suggests that it is a generalization of the usual point line geometry on the plane. That is, you take P to be the set of all points on the plane, that is R to the power 2. So this is the set of points on the XY plane. And B is the collection of lines. Line is a subset of R2 consisting of those points on that line. So this B is certainly a set family in the set of points P. So this is an example of an incidence structure. So, but this course is on combinatorics. So eventually I will move on to the finite case. So this example has infinitely many points and infinite many lines. But it has a special property from elementary or Euclidean geometry. That is, if you take two distinct points, P1, P2 on the plane, then there exists a unique line through these 2 points, that is, containing both given 2 points, P1, P2. So incidence structure generalizes this point line geometry. but this lecture is about combinatorics, so mainly I will consider the analog of such an object in finite situation. To make it finite, I restrict the set of coordinates to be, for example, just 0, 1, 2, not all real numbers. And then we obtain a point line geometry, but it's a finite analog. Okay, so let me show how it looks like. So there are only 9 points on the plane instead of infinitely many. So here's a picture. So I restrict the coordinate to be just 0, 1, 2. So the set of points 0, 0, 1, 0 up to 2, 2. So there are 9 points, and I placed them just like those are on the usual XY plane. And lines, this is a little bit tricky. You may think of usual line, but restricted to this set of 9 points. But there are some subtlety when it is not horizontal or vertical. So the set of lines are depicted in the lower part of this slide. So certainly there are 3 horizontal lines. Each line consists of 3 points. And also vertical line, each line consists of 3 points. And then there are 2 other lines. So 2 other sets of lines. One has slope -1 and the other has slope 1. But for example, if you take a line with slope 1 or maybe -1, for example, if you start drawing line from this point, then it reaches outside this set of 9 points. So what you get is a point outside for sorry. Here, this point has coordinates 3, 0. Is it not in this set of points P? But to make it uniform, I will identify this point with the origin so that this blue line has 3rd point, that is the origin. So that is the line depicted in red here. Similarly, I have another line with slope -1, that consists of these 3 points. And similar for the 3 lines with slope 1. So in this manner, I constructed the total of 3 times 4, 12 lines. And every line has exactly 3 points on it. Okay. Now it can be verified that the axiom of the one axiom of the Euclidean geometry that for distinct points, 2 distinct points, there exists a unique line in this set of 3 times 4 lines containing the given 2 points. Well, that's clear if you take 2 points with same y coordinate or same x coordinate. But if you take something else like these, well, they cannot be joined by line of slope 1, but they are joined by line with slope -1. So you can test this property for every pair of points, and it turns out there is always a unique line containing both P1 and P2. So as far as this axiom is concerned, the situation is completely analogous to the Euclidean case. It seems there is a question in the chat. What about the line passing through single point? Well, I guess you mean passing through one point with slope -1, then it will hit like this. The reason is that I would identify the point 3, 1 with 0, 1, and 4, 2 with 1, 0. You see that the identification is made in such a way that the coordinates are said to be same if they have same integer modulo 3. So 3 is reduced modulo 3 to 0, and 4 is reduced modulo 3 to 1. So that's how I identify them. Okay, I think I answered the question. So now I can proceed to the next page. Not the next page, but I have one more line before going to the next page. So, there are 4 different kinds of lines depending on the slope. So there are 12 lines, and 12 lines are partitioned into 4 parallel classes. Parallel means that they have the same slope, but you could say that they don't intersect. If you take 2 lines from different parallel classes, then two lines intersect at one point. Okay. So a parallel class just means that the collection of lines which are mutually disjoint. The organizer asked me to include application. So here is a small application. I will have more subtle application in my 3rd lecture, but here is a simple application. Now, the property I've been focusing on is that for distinct points, P1, P2, there exists a unique line in B containing both P1 and P2. Now, this set P, so far I consider the set P to be the set of points, but the P could be anything for the definition of incidence structure. So here I take P to be a set of 7 properties. So here I have P1, P2 up to P7. Those are some kind of characteristic of a person who likes football, likes classical music, and so on. And then the number 1 to 7, this may be considered as 7 different persons and his or her characteristic. So the person number 1 likes football, lives alone, and has driver's license. And number 2, a different characteristic. So what is good? What is this good for? Well, suppose you are in the police, and there are 7 suspects, possible suspects, not really a actual criminal. And suppose that the police, the police narrowed down the possible suspects to be 7 and tabulated their characteristics. And eventually, police has found that the suspect has 2 particular characteristics. The suspect has likes vegetarian food and has a bike. Now, if you look at this table, then there's a single suspect, number 4, which has both these 2 characteristics. So it is not for P3 and P5, but any 2 distinct property. If you spend time to check this, then you see that any two distinct property uniquely identifies 1 out of 7 suspects. Well, mathematically speaking, that means that for distinct P1, P2, there is a unique line. Well, line would mean that there are these 7 columns, line containing several points. In this case, it contains 3 points. And 2 points determines the unique line always. So once police identifies 2 special characteristic of a suspect, then police can identify 1 out of 7. So this is a kind of application of point line geometry arising from this particular property that 2 points determines a line. Now, let me generalize this, because mathematicians likes to generalize abstract concept. So the property I was concerned here is that for 2 distinct points, there exists a unique line in P containing P1, P2. So I would generalize this 2 points to T points. So arbitrary number T, where T is a fixed positive integer. So whenever you take T distinct points, then they exist not necessarily unique, but some constant number lambda elements B containing all of P1 to PT. So T distinct property identify exactly, well, not necessarily a single one, but exactly lambda suspects among all of them. Well, writing such a property in sentence is cumbersome. So it is wise to use mathematical notation, which I introduced earlier on the first slide. For every T in P choose T, that means T, capital T, is a T element subset of a point set P. Then this latter part of the sentence that they exist exactly lambda B in curly B containing all of P1 to PT, that means that's the size of the family of sets B in curly B containing T is exactly lambda. So using this set theoretic notation, this long sentence can be simplified in this manner. Okay. So now I come to the main definition. So here is a definition of a combinatorial design. So small t, not only t, but also take k to be a fixed positive integer. We have already defined the pair PB, an incidence structure. So P is a set and B is a set family. And I recall this property that for distinct T elements in P, they exist exactly lambda B in curly B containing all of them. And I require 2 additional property. Well, first property is not really a property, it's just a notation. It's just a definition of the symbol V. V is the size of the set P. So the set of points P will always be finite. So V is a positive integer. So I won't consider the infinitely many points on the usual Euclidean plane anymore. Only finite set of points. And the second condition is that this family B consists of subsets of a uniform size K. So in this case, this incidence structure is called a TVK lambda design, or simply T design. So important part of the definition of the design is that this sentence in italic. So whenever you take T points, there is always a lambda element B containing all of them. V and K are just symbols specifying the size of set P and size of members of B. In point line geometry, the set of the elements of P are usually called points, and the elements of B are called lines. But for traditional reason, well, this combinatorial design theory originated from statistics, and it is customary to call elements of B as blocks, while elements P are called points. Well, statisticians use different terminology. Here I will use combinatorial terminology. The points for P and blocks for elements of B. Okay. So the affine plane, well, I forgot to mention that notation AG23, but AG23 is the configuration I showed in the picture, that there are 9 points, and the each line has 3 points. So the lines are exactly blocks in this new terminology. And again, the important part is any pair of points determines single line. And 9 is the total number of points, and 3 is the number of points per line or per block. Okay. Now, this concept can be generalized to any P as long as P is a prime. So instead of just 0, 1, 2 for P equals 3 and reducing the coordinate, I mean, the identifying points modulo P, modulo 3, I can do this for modulo P. So FP will be the set of integers from 0 to P minus 1. And I consider the FP square, that's part of the plane. So there are P square points. And the lines are, as usual, lines are determined by slope. The lines with infinity of slope, those are vertical lines. That is, the x coordinate is fixed to be something A in FP, and y coordinate is arbitrary. So that's a collection of a vertical line, and then the other ones are lines with slope m. So y is equal to mx plus b. So this is completely analogous to the Euclidean geometry, but the difference is that the addition and multiplications are performed modulo p. Then it is easy to verify that this is again design. Again, the crucial property is that any 2 points you can find a line through them. Well, I guess in the middle school you probably learned how to determine the equation of a line given 2 points. And the same formula holds even for this FP square, as long as P is a prime. So that's that is usually denoted by affine plane AG to P. So that's also a 2 design with P square points. Now let me mention another application. What is the meaning of this affine plane? Well, the earlier application where there were 7 properties considered to be points are not the same as affine plane, because affine plane has 9 points. So what is the what does affine plane AG23 describe? it is the solution to the following problem. So there's a group of 9 new students selected, and suppose they don't know each other, but so I want to make them familiar with each other. So the group is divided into 3 groups of 3 students each to take a walk after lunch. Well, it doesn't matter whether they take a walk or they have a party or whatever. The kind of activity doesn't matter. But this activity should last 4 days. Now, if you think of you are a member of these 9 students, then on the first day you join one of the 3 groups to get acquainted with 2 other students. So in 4 days, eventually you get to learn. You get to know 2 times 4, 8 students. Well, 8 is exactly the number of students except yourself. So if you are lucky, then you get acquainted with all 8 other students. But is this really the case? So the question is that, can you give partition of groups for each of the 4 days so that every student gets a chance to be in the same group with every other student? Well, this AG23 gives exactly the solution to this problem. Well, there are 9 new students, so you may arrange them on the plane, affine plane, so 3 by 3 manner. And then what does this mean? So there are 4 parallel classes correspond to 4 days. And for example, suppose you are here. On the first day, you meet these 2 students. On the second day, you meet these 2 students. Third day, you meet these 2 students. Fourth day, you meet these students. Well, totally, you meet all 8 other students. This is the same for any other student you start with. You could be here, and you can check that you meet every other student in one of the 4 days. So the solution is in fact equivalent to the affine plane. And similarly, the generalized version of the affine plane, modulo P version, it gives just a solution of exactly the same problem, except that these numbers 9, 3, 3, 4 are replaced by P squared P plus 1. So AG2P has P square points. So you suppose there are P square students, and P square students are divided into P groups of P students each, and they have activity for P plus 1 days, and eventually they hope to know total P square minus 1 other students. Well, every day you get to know P minus 1 student, and there are P plus 1 days. So hopefully you get to know all the P square minus 1 other students. So that's how I rewrote the problem. So the only change is that I have replaced these numbers, P square, P plus 1. And it's quite obvious that the affine plane, or more generally, 2 design on P square points, and each line has P points, and 2 points uniquely determine 1 line, and blocks are partitioned into P plus 1 parallel classes. So you can distribute them into P plus 1 days. Then such a design gives a solution to this problem. And as I mentioned, although I didn't really prove that such a design can be constructed as an affine plane modulo a prime P. It is crucial that the P is a prime. So for example, P equals 4, that is not a prime. So it requires a different construction. But there's still there is a different construction based on the theory of finite field that belongs to the advanced algebra. Well, it depending on your level as the student at the university, you may or may not learn about finite field. So if you are familiar with finite field, you can imagine that the P equals 4 causes no difficulty in constructing the affine plane by defining lines exactly in the same manner. But P equals 6, this is not a prime either. But for this P equals 6, such a design can be shown not to exist. So some arithmetic of the number of points affects the existence of a solution to this problem. In fact, as far as I know, the existence problem is not settled for P equals 12, I think. So the problem becomes quickly very difficult as P gets large. Well, P equals 12 may not sound very large, but that is the reality. Okay, so there's a little bit more subtle problem, a very well-known problem from 1850 due to Kirkman. It is known as Kirkman-Skuger problem. So the only difference from the previous problem is that I changed the number. Here I have 15 new students, and the purpose is the same. So every day, the group is divided into 3 students each. So there must be 5 groups. And every day you get to know 2 more students. So you need 7 days to get to know 14 other students. So the problem asks whether such partition exists or not. Okay, so this was the problem posed by Kirkman, and eventually he himself solved. And the solution is, in an abstract language, this is also the same as the existence problem of a 2 design with 15 points, and every line or every block consists of 3 points, and 2 points or 2 students determine the unique line or unique block of 3 students each, in such a way that the set of all lines are partitioned into 7 parallel classes, because we have 7 days to implement this activity. So the solution is not straightforward, because we cannot make use of arithmetic modulo P. The number of students, 15, is not a square of a prime. Well, you might want to solve this problem by inspection. Well, but it is not so easy to come up with the answer. For day 1, you can just take any partition of 15 students into 5 groups of 3, but then you need to create how to partition it considerably differently on day 2, and day 3, and so on up to day 7. You might get stuck before you reach 7th day. So these are the typical application of the design theory. Now, I have a few more slides. So in the first lecture, I want to introduce the matrix technique. So in combinatorial design theory, it is often necessary to consider matrices whose rows and columns are indexed by some sets without specific ordering of elements. I'm sure if you are a university student, you have learned the matrix theory. So usually the matrices are n by n matrices, and ith row and jth column has ij entry. But here, the rows and columns are not indexed by a set of integer from 1 to n, rather some abstract finite set without specific ordering. So unless you specify the ordering of indices, you cannot actually write down the matrix, but you can still imagine matrices abstractly. So for combinatorics, well, not in entire combinatorics, but in design theory, it is quite common to use a simplified notation for the set of matrices. That is r to the power x times y. This will be the set of matrices with real entries whose rows are indexed by x and columns indexed by another set y. So the rows are indexed by x, columns indexed by y. So xy entry is denoted by the attaching subscripts x and y to the name of the matrix. Well, matrix multiplication can also be done if the second matrix has rows indexed by y, while first matrix has column indexed by y. The product is, as usual, sum over the indices. Here, the sum is not from 1 to n or something, but it's unspecified order, but it doesn't matter how you add numbers. The order don't matter, so this sum makes sense, and the product of matrices makes sense. Okay, so what is the relationship between design theory and matrices? Well, given incidence structure, you can convert it to an incidence matrix. Well, in the traditional linear algebra, you have to index rows and columns by integers, but here I don't need this. So I will index rows of a matrix M by the set of points P and columns by set of blocks B. So M will be an element of R to the power P times B. And entries are defined to be 1 or 0 according to the row index P belongs to the column index B. So M has just two distinct entries, 0 and 1. So converting incidence matrix to a metric, incidence structure to matrix is just straightforward. For example, you have seen an incidence structure of 7 points and 7 blocks in my previous example of police and suspect, and bullet just replaced by 1, and the empty box replaced by 0. So that's the concept of the incidence matrix. Now, in my previous slide, I mentioned the matrix product. So I want to multiply this incidence matrix with something else. But, well, I have only one matrix. So where is the second one? Well, second one must have a column indexed by, row indexed by the blocks at B. Well, that can be found easily to be the transpose. Whenever you have a matrix M, you can always make a product M times M transpose, because the number of columns of M is same as the number of rows of M transpose. In this case, M turns out to be the square matrix, so it doesn't matter. You could compute M square, but the M transpose has a significant combinatorial meaning. Well, if your if you have time, then you can actually compute this 7 by 7 matrix product. And it turns out that this is equal to 2i plus j, where I is the identity matrix and j is the matrix with all 1. So this means that the diagonal entries are 3 and off-diagonal entries are just 1. But what does it mean to make the product M and M transpose, where M is the incidence matrix of our instance structure? Well, rows of M and columns of M transpose are both indexed by the point set P. So let's take P1, P2 from P. Then the definition of the matrix product, and also by the definition of transpose, this counts, or this takes the sum of all product of M P1b and M P2b. But this number is either 0 or 1. So the product is 1 only if both are 1. And if you remember the definition of the incidence matrix, the entry is 1 precisely when P1 belongs to B and P2 belongs to B. So both must occur in order for this product to be 1. So this summation actually counts the number of B blocks B which contain both P1 and P2. And that was very definition of a 2 design. So if you believe me that this is a 2 design, that is 2 design with lambda equal 1, then the 2 distinct points determine a unique line or a block. So that's why the off-diagonal entries are 1. Well, this 3 may not be clear, but I will come to the discussion of this number, determination of this number. So this computation suggests that the definition of a design can be conveniently described in terms of matrix product. That is, off-diagonal entry precisely describes the number of blocks containing 2 points. So to make it precise, suppose you have an incidence structure of V points and blocks consist of only of K element sets. Then the crucial property for the definition of design is that every pair of points, distinct points, it's contained in lambda blocks. That is, the off-diagonal entry of MM transpose exactly lambda. So if you subtract lambda everywhere in the off-diagonal entry, then all the off-diagonal entries are 0. So the only non-zero possible non-zero entries are on the diagonal. So it is a diagonal matrix. So the design property can be characterized in this manner. Indeed, well, I already explained, so probably you don't need to read this again. MM transpose is precisely the number of blocks containing P1, P2. I mean, that appears in P1, P2 entry, while lambda times J minus 1, this is a matrix where with off-diagonal entry lambda constant. So equating these two is equivalent to this property, and that is same as the design property described here. Okay, but what is this diagonal matrix? In fact, this diagonal matrix can be determined when this incidence structure is a design. So here is how to determine the diagonal entry. So let me start explaining from the middle, because this middle part is somewhat unnatural. So let me start with this line. So forget about that upper part for the moment. So this line in the middle is a size of a set which consists of pair P prime and B. Well, P is a fixed point and P prime is a point different from P. So this counts the number of pairs P prime and block B such that B is a block containing both P and P prime, and P prime is different point from P. So I want to count this pair in two different ways. So let me do the easier part, that is to go down. So that is to take P prime first and count the possible B's in the second coordinate. Now P prime is required to be different from P, so we pick P prime different from P. Now given P prime, we are counting possible second coordinate, that is B. The requirement B is copied here. But this is precisely the definition, appearing in the set appearing in the definition of the design. You have 2 points, and this counts the number of blocks containing both of them. So that is exactly lambda. So this summation is taking the sum of constant number lambda. How many summons? There are B minus 1 points other than P. So that's this formula. Well, I didn't touch anything on this fraction K minus 1 in the denominator. So this manipulation in the lower half is easily explained. So this form expression at the end will be denoted by R. Now, once you learn this technique of counting pairs, then you can go the other way. Oops, sorry. The upper part. In the upper part, you take B. The requirement for B is that B is in a block, but also it contains the point P, which is fixed in the beginning. So the sum is for all B containing B. And then if you fix B and you count the possible first coordinate P prime, I copied the requirement for P prime here. So, but what is this set? This is the set of P prime in B different from P. Well, B contains P, so there are precisely K minus 1 choices for P prime, because B is a set of K elements and P has to be excluded. So this K minus 1 combined with this K minus 1 becomes 1. So you get this expression. This is the number of blocks containing a given point P, but if you remember the definition of incidence matrix, that is nothing but this number. And because this number is 0 or 1, so taking square, the value doesn't change. But then it is the PP entry of this matrix product. So PP entry of MM transpose is exactly this expression lambda, which is denoted by R. So diagonals of MM transpose are determined. Okay. So let me summarize what I proved. So R will denote this constant lambda times b minus 1 over k minus 1. And suppose M is the incidence matrix of a 2vk lambda design. Then this matrix product MM transpose has R in the diagonal and lambda in the off diagonal. So there are only two distinct entries in this product. Now, important consequence is that R is an integer. Well, R, if you look at this definition, the R looks like a rational number, but R appears as diagonal entries of an integer entry matrix M and M transpose. So R is an integer. So V, K, lambda are not completely arbitrary because this R has to be an integer. So given V, K, lambda, two VK lambda design may not exist. In fact, it doesn't exist if this parameter R is not an integer. Now, to avoid triviality, let me assume that K is less than V. K is the size of a block, and V is the total number of points. And block is a subset of the set of points. Well, if K is V, well, K cannot be bigger than V because block is contained in the set of points. But K is equal to V, but then the block coincides with the entire set of points. And there is only one such set, that is the set of points itself. So in this case, the block set consists of a singleton set, which is just a set of all points, and it is completely uninteresting. So let me assume that this is not the case in our design. So we assumed K is strictly less than V. So B consists of proper subsets of P. But in this case, this fraction is greater than 1 because V is bigger, numerator is bigger than denominator. So that means this parameter R is strictly bigger than lambda. But then it is a standard linear algebra exercise that this matrix R in the diagonal, lambda in off diagonal, and with diagonal entry lambda, R is bigger than the off diagonal entry. This matrix is invertible. Well, this matrix is same as MM transpose. So MM transpose is invertible. Well, M could be a rectangular matrix, but M times M transpose is invertible. That means this length has to be bigger than this length. Otherwise, MM trans would be not invertible, like in this case. Yeah, there's a chat in the question, how can we get 3? Well, this is here the answer. You just plug in lambda to be 1, V 7, K 4, K is 3, sorry. So 6 divided by 2, so for that particular case, the R is 3. I will mention this particular design in the second lecture as well. Yeah, so it is not immediately clear that all the diagonal entries of MM transpose are the same, but it is the same if M is the incidence matrix of a design. So the important consequence is that this length is at least this length in order for this M times M transpose is invertible. That means the number of blocks is greater than or equal to the number of points. So this important inequality is known as Fisher's inequality. Okay, so that's almost the end of the first lecture. So in the this is the last page. So here is the exercise and further reading. So in my last theorem, I mentioned that, well, not the theorem, but the statement after the theorem, that this R times I plus lambda times J minus I is invertible. And the reason is that R is greater than lambda. So find the inverse. Or more generally, well, this R times I times lambda times J minus I is a linear combination of the matrices I and J. So, or more generally, consider arbitrary linear combination of the identity matrix and the all one matrix, J. So J is the matrix with where everywhere you have one. So the exercise to determine when the V by V matrix AI plus BJ is invertible. And when it is, find the inverse. So this is a algebra. This is an exercise in matrix algebra. The hint is that if you square the all one matrix J, then it becomes V times J. So J satisfies very simple quadratic equation, and this can help you to find the inverse and also find the criteria for invertibility. Okay, so that's more or less the end of the first lecture. So I have two standard books that introduce the theory of combinatorial designs. The first is really the title says Introduction to Combinatorial Design due to Walter Wallace, published in 2007. And the second is a book directed to more experts in design theory. It's a huge book, consists of 2 volumes. Each volume is already quite thick. So this is written by 3 German mathematicians, Beth, Jungnickel, and Lenz. The title is Design Theory. Okay, and third, this is not really a book, it's just a Wikipedia page that explains very rather complicated history of Kirkman-Skuger problem. I think it's better to read the Wikipedia page instead of for me explaining the history, because the Wikipedia page is a very describe very precise history of this problem. Okay, that's the end of the first lecture. So I suggest we take a break for maybe 8 minutes. We resume at 15 past. Well, depend on your time zone.
Okay, thank you, Professor Munemasa. So we will take a break now. As usual, we have a video for around maybe 10 minutes. So after we finish the video, maybe we can start the second session.
Yeah, you mean the video? What do you mean?
From us. Yes. Okay, so let's take a break, and we will back for another 10 minutes later.
Yeah.
Okay. Thank you, everyone. Thank you, Professor.
So yeah, see you soon.
Established in 1920 with the name Technische Hogeschool te Bandung, Institut Teknologi Bandung is the oldest technical university in Indonesia. The 3rd of July 2020 is marked as Institut Teknologi Bandung's 1-century existence. The establishment of this long-established institution is recorded in history as the founding of Indonesian technical higher education and the pioneer in the advancement of science and technology in Indonesia. Located in Bandung, West Java, Indonesia, precisely on Ganesa Street, number 10, ITB currently has 12 faculties, 29 undergraduate programs, 52 master's programs, 26 doctoral programs, and 2 professional programs. Other than the campus site located in Ganesa, ITB's campuses are also located in Jatinangor and Cirebon. 39 programs have been international accredited from accreditation boards around the world, namely from the United States of America, ASEAN, Germany, Japan, the United Kingdom, South Korea, and the number of accredited programs is expected to increase in the near future. ITB has been developing its cutting-edge research through the 102 research groups from 12 faculties and schools, 24 centers, 7 research centers, and 5 centers of excellence. To date, ITB has also established 104 startups, 315 intellectual property rights, and 137 innovations. In the spirit of In Harmonia Progressio, ITB alumni have worked and excelled in various fields and sectors. For instance, Insinyur Soekarno as the first president of the Republic of Indonesia, B.J. Habibie as the third president, Iskandar Ali Shahbana as the father of the communication system in Indonesia.
Fakultas Matematika dan Ilmu Pengetahuan Alam Institut Teknologi Bandung atau disingkat FMIPA ITB merupakan fakultas yang menyediakan program studi berakreditasi unggul dan terbaik di Indonesia bagi mereka yang ingin mendalami pengetahuan di bidang kimia, fisika, astronomi, dan matematika. FMIPA ITB merupakan yang tertua dan terdepan di Indonesia di bidang matematika dan ilmu pengetahuan alam dengan reputasi yang sudah diakui secara nasional dan internasional. Sebanyak 20 program studi yang ditawarkan terakreditasi A atau unggul oleh Badan Akreditasi Nasional Perguruan Tinggi. Dan keempat program studi di tingkat sarjana mendapatkan akreditasi bergengsi secara internasional. Setiap tahun, FMIPA ITB mendidik lebih dari 2.300 siswa, baik di tingkat sarjana, S2 maupun S3. Dalam memberikan pengajaran berkualitas, dosen-dosen FMIPA ITB didukung oleh 16 kelompok keilmuan yang aktif melakukan berbagai penelitian. Kelompok keilmuan astronomi bertujuan untuk mengembangkan ilmu astronomi, astrofisika, ilmu luar angkasa, dan ilmu lain yang berhubungan dengan astronomi. 6 kelompok keilmuan fisika aktif melakukan riset tentang bumi dan sistem kompleksnya, tentang material-material yang ada di alam dan pemanfaatannya, tentang material magnet dan fotonik serta pengembangannya, dan banyak lagi lainnya. Di bidang kimia, 4 kelompok keilmuan secara produktif mencari temuan-temuan baru untuk pengembangan, penerapan, dan penyebarluasan ilmu kimia, serta penyelesaian berbagai masalah yang berkaitan dengan kimia di masyarakat. Begitu juga dengan 5 kelompok keilmuan matematika, di mana para dosen di dalamnya mendukung proses pembelajaran matematika, serta pengembangan dan penerapan matematika di dunia modern saat ini melalui penelitian mereka. Proses pembelajaran dan kegiatan riset di FMIPA ITB didukung oleh fasilitas-fasilitas mumpuni yang dimiliki oleh fakultas. Observatorium Boscha merupakan observatorium modern tertua di Indonesia dan Asia Tenggara, sehingga memiliki peran yang sangat penting di dunia dalam pengamatan dan eksplorasi benda-benda angkasa. Laboratorium Fisika Terpadu dan Laboratorium Kimia Terpadu di FMIPA ITB memungkinkan para peneliti dari kelompok keilmuan yang berbeda-beda untuk dapat mengakses berbagai peralatan penelitian di satu lokasi saja, yaitu di masing-masing laboratorium terpadu tersebut. FMIPA ITB memiliki deretan kontribusi nyata dalam memajukan ilmu pengetahuan yang dinikmati oleh mahasiswa, masyarakat, dan juga industri. Bagi mahasiswa, komitmen FMIPA ITB dalam mendukung mahasiswa memaksimalkan kompetensi, ternyata kan melalui upaya untuk secara rutin mengirimkan mahasiswa ke ajang kompetisi internasional yang sangat bergengsi seperti Olimpiade Matematika.
FMIPA ITB memfasilitasi mahasiswa FMIPA untuk berkompetisi pada tingkat nasional maupun internasional. Fasilitas yang disediakan berupa pembinaan dan akomodasi yang meliputi biaya maupun tempat pelaksanaan. Pada tahun 2021, FMIPA mengirimkan 5
Okay, Professor Munemasa, are you ready to the next session?
Okay.
Okay, thank you.
Okay, just a minute. I will share my screen. Okay, can you see the slides for the second lecture?
Yes, clearly.
Okay. So let me begin the second lecture. Second lecture, I have only 13 slides, so it will be a little shorter, hopefully, than the first, so that I can finish on time. So this is the final, essentially the same as the final slide, where I proved Fisher's inequality. Well, not quite proved, but I left some parts as exercise to show the invertibility. But the modulo that exercise, this theorem is proved. And the diagonal entry, well, in fact, one of the people in the audience asked about this diagonal entry. Diagonal entry is constant R if M is the incidence matrix of a 2 VK lambda design. And this constant R is lambda times B minus 1 over K minus 1. So this R is the diagonal entry, and diagonal entry, if you remember the definition of the incidence matrix, this is the number of blocks P containing a given point P. And this P, this number does not depend on P. But this means that the 2 VK lambda design is automatically 1 VK R design. Remember that this parameter VK don't change because we have the same set of points and same set of blocks. The condition for design is that here I take only one point and count the number of blocks, and turns out to be R. So that is reflected to these numbers 1 and R. So 2 VK lambda design is automatically 1 VK R design, where R is given by this number. Okay. Now, this is the inequalities. So you may think of this as a lower bound for the number of blocks. Just one second. Sorry. So for certain design, this equality may hold. And when equality holds, then such a design is called symmetric. Symmetric design has rather special property, which is not valid for general design. So for the next few slides, let me talk about the properties of symmetric design. Well, by definition, a design is symmetric if you have equal number of points and blocks. the Fisher inequality says the number of blocks is always at least the number of points. Okay, but what is the number of blocks? It can be computed using these v, k, and lambda, and the formula is this one, lambda times v minus 1 divided by k minus 1. And why is this? Well, here I use the same kind of technique of counting, which I showed in the first lecture. So I consider certain sets, a subset of a direct product, and count the number of elements in two different ways. So here I create the sets consisting of triples P1, P2, and B. P1, P2 are points, and B is a block, and P1, P2 belongs to B, and P1, P2 are different points. So first way to compute this is to consider P1, P2 first. Okay, P1 runs through set of points P that contributes to this factor V. Now, once P1 is chosen, P2 has to avoid P1. So the number of choice for P2 is V minus 1. Now, both P1 and P2 are specified, then the number of choice for B is determined by this condition that is precisely the defining condition for the two design, and that is equal to lambda. So that's the first way. Second way will give the right-hand side. In the second way, you compute in the opposite order. First, take B. Certainly, there are this many ways to choose B. Once B is chosen, then you are free to choose 2 points in B as long as they are different. Well, this is a 2BK lambda design. So K is the size of the block B. So there are K ways to choose P1. And then once P1 is chosen, there are K minus 1 remaining points on B. So that's the other way of counting this set. And we are counting the same set in 2 ways, so they are equal. So dividing both sides by K minus 1, we get this formula. So this is the number of blocks in a design, not necessarily symmetric. What happens if the design is symmetric? Well, symmetric means the number of points is same as the number of blocks. The number of points is V. So if the number of points is same as the number of blocks, then this B is same as V, so you can cancel these. And if you multiply both sides by K minus 1, you get this formula. But now R was lambda times V minus 1 divided by K minus 1. So if you divide this formula by K minus 1, then you get R on the left-hand side, K on the right-hand side. So this condition is equivalent to R is equal to K. So this is an alternative definition of design being symmetric. I will later use this condition for symmetric design. Now, for symmetric design, the incidence matrix is a square matrix, and this property can be used to derive further interesting property of symmetric designs. And recall that R is the number of blocks containing a given point, and K is the size of each block. So it looks quite the definition looks quite similar, but R counts the number of blocks and K counts the number of points. Oh, sorry, there is a typo. This should be P. Now, in terms of the incidence matrix M, it is just the row sum and column sum of M. M is a matrix with entries 0 and 1 only. So if you count, if you take the row sum, then it counts the number of ones in that row. So what does it mean? You take a row of M and count the number of 1. So that means you fix a point P and count the number of blocks containing P. And that is exactly this number. So R is the row sum of P. And similarly, the column sum, if you fix a block P and count how many ones appear in that column, then that is same as counting the number of points in that block. So that is K. Okay, so I get R for the row sum, K for the column sum. So that means in terms of matrix product, taking column sum is same as multiplying all one matrix or all one vector from the right. So these two properties can be conveniently expressed in terms of the matrix equation. M times or one matrix J is R times J, that is taking the row sum, and J times M, that is taking column sum, you get K times J. For symmetric designs, one characterization of a symmetric design was that R is equal to K. So for symmetric design, these two products coincide. So MJ is same as JN. Usually we say that we describe this that M and J commute. And this property it's used in the next slide to derive an important property of a symmetric design. As follows. For symmetric design, we have seen that the M is invertible. Well, because M times M transpose was invertible. So M inverse exists. So if M inverse exists, then we can move this M to left-hand side, that M to right-hand side by taking inverse, so resulting in this this formula. Okay, so M inverse commute with J because M commutes with J. Now M transpose is equal to Ri plus lambda times J minus I. That was established in the theorem. Well, this holds even if the design is not symmetric. But if design is symmetric, then M is invertible. So I can remove this M and put it on the left-hand side by taking inverse. So that's how I did this. Now M inverse commute with J, and obviously any metric commute with I. So M inverse commute with J minus I. So I change the order of the product here. But then I can multiply M from the right. Then this M inverse goes to the left-hand side, but from the right. And then I get back to the same formula, R times, sorry, another misprint. R times identity plus J, lambda times J minus I. But what is the meaning of M transpose M? M transpose has rows indexed by the set of blocks, and same for columns of M. So the entries of M transpose M is just the number of points common in lambda. So B prime entry, when you take different B and B prime, then M transpose M, the off-diagonal entry is lambda, so that is lambda. So it means that the two distinct blocks intersect with lambda points. So this is a very special property which is valid only for symmetric design, but not general to design. So if you write down in sentence, this looks quite similar to the very definition of a to design. Here I first wrote the defining condition for the to design. That is, for two distinct points, they exist exactly lambda blocks containing both P and P prime. That is the definition of to design. And second line, I'm writing the consequence obtainable from the design being symmetric. That is, whenever you take distinct B and B prime, then they intersect at lambda points. To state differently, it means there are exactly lambda points in the intersection. So you see, if you compare these two sentences, then the points and blocks are just switched, and this containment relation are also reversed. But the two condition looks quite similar. In mathematics, usually such a phenomenon is called the duality property, and this is why the name of symmetric design come from, because these two conditions are symmetric to each other when points and blocks are reversed. Now, from this condition, it is quite obvious that our first example of to design, affine plane AG23, is not symmetric, because we have seen there are parallel lines. Parallel lines do not intersect. So this would be empty, so there cannot exist. So it violates the second condition. Of course, you can argue in a different manner, just checking the defining condition for the symmetric design, that the number of points and number of blocks, if you remember how many points are there and how many blocks there are, then it turns out they are different. So it is not symmetric. Now, to get the example of symmetric design, let me introduce another construction, projective spaces and projective plane. Well, actually, we have seen an example of projective plane. In general, symmetric design with this lambda equals to 1 is called a projective plane. There's a characterizing condition for symmetric design, that is this equality. Yeah, but the lambda is equal to 1, so this lambda disappears. So B minus 1 equals K times K minus 1. So in other words, B is equal to K squared minus K plus 1. So the projective plane can be expressed by a single number K, because V can be expressed in terms of K. And not the K itself, but the number K minus 1 is called the order of the projected plane. For example, the projected plane of order 2, so you take K to be 3, then B is 7, and so it is a 2, 7, 3, 1 design. And because this is a symmetric design, not only the points, but also blocks has 7 members. And we have already seen the incidence metrics. It turns out that this incidence metric came from my earlier example of characteristics and suspects. So there are 7 properties and 7 suspects, and that was precisely the incidence metrics of a projected plane of order 2. That is a 2, 7, 3, 1 design. Now, but how can we come up with such a design? Well, for that, I need a binary operation, binary addition. So in general, projective spaces can be defined in a much more general context, but here I only consider projective space over F2. F2 is the set consists of just 0, 1 only, because in the affine plane, I consider the set 0, 1, 2, and that is denoted by F3. So consider the set of points that consists of n-dimensional vector whose entries are just 0 and 1, but except the 0 vector. Yeah, there's a question, projected plane in the sense of geometry, certainly. Parallel lines do intersect. Yeah. Well, you will see why, and you will see soon that the all pairs of lines intersect at one point. And so this, if you don't remove 0 points, then you may think of this as an n-dimensional vector space, but the coordinates are restricted to 0 and 1. And the set of blocks are triples of the form x, y, and x plus y. So x and y are arbitrary but distinct points, and then x plus y is another point. And that will be different from x or y because x and y are non-zero. But remember that the addition is performed modulo 2, so you only get 0 and 1. 1 plus 1 is 0. And another way of describing the set of blocks is that this triples consisting of x, y, z, such that their sum is 0. Because addition is modulo 2, x plus y plus z is 0, that means z is same as x plus y. And it turns out that this gives a 2 design, and known as the projective space over F2. Well, why is this a 2? Why is this a 2 design? First of all, the number of points is clearly, well, yeah, here is an explanation. So let's check the defining property of the 2 design. That is, you pick 2 points, then it is clear that you name these 2 points x and y, and there is certainly a block containing x, y. That is, you add the 3rd point, x plus y, then it is a block. Is this a unique block? Well, it has to be a unique block because if there is a block, then the 3 points must sum to 0. So the third point is uniquely determined by the first two. So given xy, this z is uniquely determined to be x plus y. So for any distinct 2 points, there is a unique block containing both x and y. So that verifies the defining property of the two design, that is 2 determines unique block. And the rest, these two are straightforward because the total number of points is 2 to the power n for this set, minus 1 corresponding to the removal of the z origin. And it is clear from the construction that every block consists of 3 points. So 3 points, so it corresponds to this specification. So you get two design known as the projective space. Now, for the special case where n equals 3, so if n is equal to 3, then the number of points is 7. So you get a 2, 7, 3, 1 design. And that is known as projective plane of order 2. So this is a 2, 7, 3, 1 design, and you can check the characterizing property of the symmetric design, that is, compute the number of blocks or determine the number r from vk lambda. You can verify that this is indeed a symmetric design. So here's a picture of the projectable plane of order 2. So to get the projective plane, I have to take n to be 3. So the elements of the point set are non-zero vector, 3-dimensional vectors, except 0 vector. And b, I didn't change anything for b. And so there are 7 non-zero vectors of dimension 3, and they are depicted in this picture. And the lines in this picture, as well as the circle in the middle, represent blocks. For example, let's look at this 3 points. If you add 0, 1, 0, and 1, 0, 1, you get 1, 1, 1. So these 3 points form a block. And likewise, you can verify that these 3 points, and these 3 points, and these 3, these 3, and these 3, and these 3. So there are a total of 6 straight lines. And in addition, these 3 points on this circle, it's again a line. So there are 7 blocks represented by 6 lines and 1 circle. And from the picture, you can see that the 2 properties of the design, whenever you take 2 points, then there's a unique block or unique line through these 2 points. For example, if you take 2 points, then there's a unique block. That's the first property, that is the defining condition for the 2 design. The second property at the bottom is that consequence of this design being a symmetric design, that is, whenever you take 2 blocks, then there exists a unique point. That is, you take 2 lines, then it meets in exactly 1 point. take two lines, they meet exactly 1 point. So this configuration satisfied both of these two properties. Now, yeah, so there's a comment that these blocks are just linearly dependent vectors. Yes, that's quite correct. So in this, if you are familiar with the field operation, then here I don't allow any scalar other than 0 and 1. So linear combination, the only possible linear combination is just taking a sum. So the only occasion where three vectors could be linearly dependent is that they sum to 0. So B is precisely the set of three vectors which are linearly dependent. So that is the set of blocks, another way of describing the set of blocks. Okay, so the next topic is the complement of the design. So by complement, I mean for each block, I consider the complement of the set of that set inside the set of points. Each block is a subset of a point set P, so this is the complement. Obviously, there is one-to-one by correspondence between the original set of blocks and this B to the power C, this complementary sets of blocks. And this B to the power C is another set family. So you may think of this as another incidence structure. In fact, it is a design. So replacing this block set B by B to the power C, this incidence structure is called a complement. And it turns out that if you have start with a two design, then it is also a two design. Okay, but the numbers are different. Well, the number of points remains the same because we take the same set of points. The blocks size are different because we take the complement. B is a k element set, so taking the complement, you get V minus k element sets. So these two are easy to verify. A little bit difficult is to compute this number lambda prime, which is different in general from lambda. So lambda prime turns out to be this number. I will prove this in the next slide. Yeah, okay. But to do that, I need to recall this symbol R, definition of this quantity R, which is lambda times V minus 1 divided by K minus 1. And the R is the number of blocks containing a given point. That was the number R. Now, using this R, because R appears here, the proof for the proof of this expression, you need to understand the meaning of R. So using this, it is straightforward to establish this formula. Let's see why. Here is how. So I need to verify that two design property for this set family B complement. So to do that, I take two distinct points, P and P prime, and count the number of blocks in B complement, that is, count the number of blocks in B complement containing these 2 points, P and P prime. But what does it mean for this set to contain P and P prime? That is same as the B does not contain P prime. So we are just counting the number of blocks B not containing P or P prime. Well, if you negate this condition, then this means B contains one of P or P prime, at least one of them. So we need to find the number of blocks containing at least one of P or P prime. And that can be computed. I mean, this looks a bit long expression, but it's intuitively easy to imagine by this Venn diagram. So I consider the set of all blocks and partition this set of blocks into 4 parts, depending on the block containing both P, P prime. That is intersection of the set of all blocks containing P, and all block containing P prime. And outside the union of these 2 sets of blocks is that those blocks not containing P, P prime. Yeah. So what I want to compute is that this one that is outside this part. So that is same as saying that taking difference from entire set of blocks, the union of this part. That union is R plus R minus lambda, because R is the size of this left part and R is the size of the right part. The intersection is lambda. So this union has to have R plus R minus lambda. And that gives the formula for lambda prime. Okay, so the complement of the design, 2 design is again a 2 design, but the lambda is replaced by lambda prime. Okay, so here is the summary of what I proved. So let PB be a 2 BK lambda design. Okay, then the complement is a 2 B minus K. That was lambda prime I established design. And it is clear that if PB is a symmetric design, that is the number of points is same as the number of blocks, then so is its complement. Yeah, this is because there is a 1-to-1 correspondence between B and BC. So passing the complement, the number of blocks doesn't change. So the property of symmetric is preserved. Okay. So let's apply this theorem for the projective plane of order 2. Projective plane of order 2 has 7 points, and each line or each block has size 3. And it is a 2, 7, 3, 1 design. So V is 7, K 3, block size, the number of block is also 7, same as V. And R is same as K because it is a symmetric design, and lambda is 1. Now, what is lambda prime? I need to compute lambda prime. Lambda prime is 7 minus 2 times 3, that's 1, plus 1, that is 2. And this 4 was the difference of V and K, so 7 minus 3, so that's 4. And project plane of order 2 is a symmetric design, so its complement is also symmetric. So in this manner, we obtain a symmetric 2, 7, 4, 2 design. Now, for symmetric designs have extra property which is not shared by general 2 design. That is the second property. That is, for 2 distinct blocks, there are exactly lambda points in common. In this case, well, lambda is, well, it's same as lambda prime because here I'm considering, sorry, this in strictly speaking, I'm applying this condition for the complement. So this 7, 4, 2 design. So that is this 2 appears here and here. So in terms of picture, we have this following. So if you take 2 points, P and P prime, then there are 2 blocks containing both. So I have B and B prime, both containing P and P prime. On the other hand, if you forget about this P, but start with the 2 distinct blocks B and B prime, then there are exactly 2 points in common. So yeah, you do have 2 points always in common. So that's the important property which I'm going to use in the next lecture for application. So in the complement of the projected plane of order 2, you get 2, 7, 4, 2 design. And it has not only the property of the 2 design, but the dual property that is a consequence of a symmetric design, that 2 blocks intersect in 2 points. Okay. Now the final lecture, the third lecture, I will discuss the following interesting problem. Now it is not about police trying to catch a suspect among 7 possible suspects, but it looks somewhat similar. So suppose that you are given a set P of 7 unknown but distinct substances. So name them P1, P2 up to P7. Okay. Among these 7 substances, exactly 2 are potentially dangerous in the sense that they explode when mixed. But you don't know which 2 are those dangerous ones. So you want to find these 2 among 7 by mixing actually some of the substance in the safe underground facility, so no one gets injured. Yeah, there's no way to tell which 2 are the dangerous one unless you actually make them explode. Okay, and we assume that you have sufficient supply of these 7 substances, although you don't know which 2 are dangerous. So you may use the facility as many times as you wish, so you can test them as many times as you wish. In principle, you may choose every pair of 7 to test 7 choose 2 21 times. Then exactly 1 test out of 21, the explosion will occur, and you know the answer. You know exactly which pair are the dangerous pair. Okay, well, but unfortunately, it is expensive to use that facility because it's a solid underground facility. So you need to pay some fee to use that. So you want to minimize the number of tests. Okay. Now, fortunately, the facility can not only take 2, but up to 4 substances at the same time. Well, if you mix 4 of them, but if they contain 2 dangerous ones, the explosion will occur. Okay. The existence of extra 1 or 2 substance doesn't affect the result. Okay, so taking advantage of mixing up to as many as 4 substances, you want to minimize the number of tests. Well, you need to fix the entire plan of tests before you begin the first test. So it is not allowed that you observe first few tests and then make the next plan after that. No, this is not allowed. You need to fix the entire plan of test before you begin the first test. Okay, so that's the rule. Okay, so how can we minimize the number of tests? Well, if you are maybe some clever guy that 21 is not necessary, but 20 is already sufficient. You see the reason? Well, if no explosion occur after 20 tests, then there's only one remaining pair, and that was the dangerous pair. And if explosion occur in the first 20 tests, then you already know which two are dangerous one. So you don't have to use the test facility 21 times, but 20 is enough. But still quite large. So I'll leave you to spend some few minutes to think about this situation and how small you can be. Probably you may not reach the answer, but I will give you the answer in the next lecture. Okay, so that's all for the second lecture. So let us take a break for, I don't know, 5 minutes or 10 minutes. I don't know.
Okay, 5 minutes.
It's up to you. Okay.
It's okay. Yes. Thank you, Professor Munemasa. So we will begin the last lecture for 5 minutes later. Also for everyone, we already put the slides of Professor Munemasa's lecture today. So you can also check the slides at the CPND. We already put in there, so please kindly check the CPND.
Yeah, there's a question at the end. When we mix 4 of them, well, if these 4 contains 2 dangerous ones, then explosion will occur. But certainly we do not know which of the 2 out of these 4 are the dangerous one. Okay, does it answer the question? Well, if you have different combination, then you may be able to tell which 2 are really the dangerous one.
Okay, I think I think it answered the questions. Okay,
Good.
everyone, let's start the lecture 5 minutes later after. Let's take a break.
MIPA untuk berkompetisi pada tingkat nasional maupun internasional. Fasilitas yang disediakan berupa pembinaan dan akomodasi yang meliputi biaya maupun tempat pelaksanaan. Pada tahun 2021, FMIPA mengirimkan 5 mahasiswa pada kompetisi matematika internasional IMC 2021 dan berhasil mendapatkan 2 emas, 2 perak, dan 1 honorable mention.
Bagi masyarakat, lewat kelompok-kelompok keilmuan, dosen dan staf FMIPA ITB giat menjalankan pengabdian masyarakat yang sangat membanggakan fakultas.
Observatorium Bosca bersama dengan program studi dan kelompok keahlian astronomi di FMIPA ITB mengupayakan agar konsep-konsep dasar sains yang berkenaan dengan astronomi itu dapat menjadi bagian dari hidup masyarakat yang terintegrasi. Observatorium Bosca dengan dukungan FMIPA bekerja sama dengan banyak pihak, bisa NGO, bisa industri, bisa korporasi. Jadi ada banyak yang bekerja sama mendukung program pendidikan astronomi dan menyediakan sumber belajar yang tidak ada batasnya. Karena peran Observatorium Bosca dan astronomi di ITB di bawah FMIPA ini ada banyak sekali yang berhubungan langsung dengan masyarakat. Umpamanya saja pengamatan bulan baru, hilal, bagaimana hari-hari penting itu ditentukan, banyak sekali kontribusi dari Observatorium Bosca.
Kami telah banyak kerjasama dengan berbagai instansi pemerintah pusat dan daerah, pihak swasta dan industri di dalam maupun luar negeri untuk memajukan pendidikan, penelitian, dan pengabdian masyarakat. Kita telah juga membuka layanan penggunaan alat lab bagi masyarakat luas, diantaranya SEM, Microcity, NMR, alat praktikum pengajaran, dan HPC yang ada di gedung BSCA, dan juga peralatan lain yang tersebar di gedung Prodi dan juga Observatorium Bosca. Dengan peralatan ini, kami telah memberikan pelayanan dalam bidang pendidikan, penelitian, dan industri. Kerjasama dalam bidang penyelenggaraan beasiswa pasca sarjana juga telah kita lakukan, diantaranya penyelenggaraan pendidikan S2 pengajaran bagi guru, di Departemen Agama dan juga Provinsi Bangka Belitung dan akan menyusul beberapa Pemda lainnya. S2 dalam bidang aktuaria untuk staf BPJS Ketenagakerjaan dan pendidikan S2 Master by Research dan Doktor by Research di lingkungan organisasi penelitian BRIN. Pendidikan S3 bagi staf Kementerian Perdagangan dan lainnya. Kami juga sangat concern dalam upaya membantu meningkatkan kualitas pendidikan menengah dan dasar yang diramu dalam program peningkatan kompetensi guru dan siswa, memberikan pelatihan bagi para laboran atau teknisi, penyiapan bahan ajar, modul praktikum, dan lainnya. Kami siap bekerja sama.
Sementara kiprah FMIPA ITB bagi industri hadir dalam bentuk kinerja riset dan inovasinya.
Pada saat awal pandemi COVID-19, kami kemudian diminta oleh BPPT BRIN untuk mengembangkan alat uji cepat deteksi antibodi COVID-19. Nah, kami bersama-sama peneliti di FMIPA, kemudian SCTH, dan juga mitra industri kami, PT Pakar Biomedika Indonesia, didukung oleh BPPT BRIN dan juga tentu saja FMIPA, kami mengembangkan alat uji cepat untuk deteksi antibodi COVID-19. Alat yang dihasilkan dinamakan e-COVID-19, saat ini sudah tervalidasi dari FK Unpad dan kami sedang melakukan pengajuan izin edar.
Dalam hal pendidikan, khususnya untuk peningkatan SDM dari industri itu, untuk saat ini kita berfokus pada peningkatan SDM dari industri keuangan dan juga peningkatan SDM di industri alat-alat berat ya, khususnya untuk pengolahan data besar. Bekerja sama dengan BPJS Tenaga Kerja, di sini kami sudah bisa memberikan kontribusi bagi dunia industri dengan meluluskan sebanyak 5 staf dari BPJS Tenaga Kerjaan di dalam bidang asuransi. Demikian juga di industri alat-alat berat, di sini kami juga memberikan pelatihan bagi SDM PT Komatsu Indonesia dalam rangka mempersiapkan mereka untuk memberikan pelatihan di manajemen bisnis ya, untuk mendapatkan Deming Prize.
FMIPA ITB secara berkesinambungan aktif berkontribusi dalam pengembangan dan penerapan matematika serta ilmu pengetahuan alam untuk kesejahteraan masyarakat Indonesia. Bergabunglah dengan kami dan kembangkan potensi Anda secara maksimal.
Can I begin this final part?
Okay, yes, we can start to the next part, last part.
Okay.
Please, Professor, yes.
Okay. So this is the third part. So I will continue with the problem I asked at the end of the second lecture. So the problem is to minimize the number of tests, and the facility can mix up to 4 substances at the same time. So how can you take advantage of this fact to reduce the number of tests? Okay. I hope everyone understand the meaning of the problem. So there are 7 substances, and you may think of this as the points of the incidence structure. And the test, you need to select up to 4 substances or 4 points. So it may not be exactly the design because the size of blocks or blocks are just the collection of substances which are used in the test. So there may be several tests, of course, up to say 21 tests, for example. Then you need to create the set family once you create the plan of tests. So here is a more abstract description. So let B1, B2, and so on be the collection of substances mixed in the first and second, and so on tests. Now, since the facility can mix up to 4 substances at the same time, so this set family consists of sets of size 2, 3, or 4, but not 5 or more. Well, for the obvious reason, I don't allow this set to have 1 or less elements. And I also assume that they are distinct. Why? Well, because there is no point of repeating the same tests with the same selection of substances because we already know the result. And also, it doesn't make sense to put only 1 substance in a test because we know for sure that no explosion will occur, and even less for empty set. So this is the set family. The plan of test can be regarded as an incidence structure or set family consisting of sets of size 2, 3, or 4 of a 7-element set. But what is the requirement? We need to be able to tell which 2 out of 7 are dangerous pairs. Well, to describe the requirement, it's better to first create a matrix whose rows are indexed by pairs of substances, columns are indexed by blocks. And again, it is just look like a incidence structure, but it is different from the incidence matrix because the rows are indexed by, not by P, but P choose 2. So when you take pair T from P choose 2, then, and also when you take a block B from this incidence structure, then T may or may not be contained in B. And so the matrix has entry 1 or 0 according to T is contained in B or not. So we create a matrix whose entries are just 0 and 1. And because we are required to create the entire plan before you actually perform the test, so you actually create this matrix before you begin the test. Okay, so the rows are indexed by P choose 2, so there are 21 row vectors. And the row vectors have entry 0 and 1. We don't know how many columns are there, but we want to minimize the number of columns because we want to minimize the number of tests. Now it's possible to describe the requirement. That is, requirement is to be able to tell which to tell the unique dangerous T0, that is the pair of 2 substances, which is originally not known to us, but which will be known to us as a result of the test. Okay. Now, the definition of the matrix N is given here. Let's look at the row T0. We don't know what T0 is, but the definition is still valid. And what is the meaning of this row vector? When the test mixing substance in block B is performed, the B contains this dangerous pair T0. So the result of this test is the explosion. So the one on that particular row means explosion as a result of the experiment, and 0 otherwise, that is, if B doesn't contain the dangerous pair. Okay, so the row vector will mean the result of the test, provided that row T0, that row corresponding to T0 is in fact a dangerous one. Okay, now if the row of N corresponding to T0 is different from any other row of N, then we can uniquely define T0. Okay, I mean, you create the plan that is the set family B, then you can create this matrix N. Then according to the plan, you perform the test, then you get some result. Well, sometimes it explodes and sometimes doesn't explode. So you get the row vector as a result of the test. Okay, the row vector, that row vector coincides the row of N corresponding T0, and the row vector of N corresponding to T0 is different from any other row of N. Then you see the result has to be caused by the T0 being the dangerous pair. Because if other T is a dangerous pair, you would have gotten a different result. So the requirement is that the row of T0 is different from any other row of N, of N. Okay, but you don't know T0 beforehand. So this property must be guaranteed for every T. That is, the row vectors of N should be pairwise distinct. Right? After performing the test, then the result, you get some row vector, and the row vector must coincide with one of the row vectors of N, and it must coincide with exactly one row vector of N. So the index T corresponding to that row vector is the dangerous pair. So that is precisely that precisely describes the requirement that the row vectors of N should be pairwise distinct. Well, if the number of tests is small, then the vectors are short. So you may not be able to have this property. Okay, let me state the problem once again. So P is a set of 7 substances, or 7 points, and B is a set family consisting of 2, 3, or 4 element subsets of P. The problem is to find the smallest cardinality of this set family such that the matrix N, defined by 1, 0, depending on T and B or not, has pairwise distinct row vectors. Those are indexed by T, where T runs through P choose 2. I should write T through P choose 2. So there are 21 row vectors. So N should have 21 distinct row vectors. That means the number of columns cannot be too small, because N has 7 choose 2, that is 21 distinct row vectors, but the N has just entry 0 and 1. So what is the total number of vectors? 0, 1 entries, and the number of columns, or the number of entry of the vector, is the size of B. There must be sufficiently many distinct vectors to fill the rows of N. That is at least 7 choose 2, 21. So 2 to the power, the number of coordinates, that is the number of distinct vectors possibly used in N, is at least 21. Okay, what is the smallest power of 2 bigger than or equal to 21? That is 32. So 2 to the power 5. So you need at least 5 tests to be able to tell exactly what the outcome, what the dangerous pair is. Okay. Okay, we learned projective plane of order 2. So, so you might want to use this. Well, this is a 7-point incidence structure, and every block has size 3, so it could be used as plan of test. But it turns out that this is a bad choice. Why? Yeah, because indeed, let T0 be a dangerous pair, say. So it's 2 substances out of 7. So suppose you have 2 substances out of 7, and then there exists a unique block B0 containing T0. So here is B0. Okay. But B0 contains 2 other pairs. For example, B0 contains this T1. So you don't know which pair caused the explosion when the test is performed for B0. B0 contains 3 substances, and in particular 2 dangerous substances, T0, but you don't know that T0 caused the explosion or T1 caused the explosion, because B0 contains 3. So the test will show B0 is positive, and it turns out no other block showed positive because T0 is not contained in any other block. That is the property of the projective plane, that the 2 points in T0 are contained exactly in this unique block and no other block. So no other block gives positive test. But then T1, you get the same result. T2, get the same result. So you cannot distinguish T0 from T1, T2. So after performing the total of 7 tests, corresponding to 7 blocks of projective plane of order 2, you still have 3 substances. Out of 2 are dangerous, but you don't know which 2 are dangerous. So that's why it is a bad choice. It certainly doesn't satisfy the requirement. But we learned the complement of a projective plane. Complement is a 2742 design, and it has following properties that is easily described in terms of picture. First, it is a 2 design, so whenever you take 2 points P and P prime, then there are exactly 2 blocks B and B prime. And two distinct points, B and B prime, they meet at exactly 2 points. So we use these properties to show that if you take B to be this complement of the projected plane, that N has pairwise distinct rows. Remember, this complement of the projected plane just have 7 blocks. So it is significantly smaller than 21. So you save the cost by cutting it in 1/3. Okay, why enhanced pairwise distinct rows? Okay, so for distinct, so these two are properties of the 2742 design, that is a complement of the projected plane. Okay, so I rewrote it in a short manner, in more using mathematical symbol or set theoretic notation. So the first property is the design property that any pair or any T two-element set contained in exactly 2 blocks, and the second is the intersection of 2 blocks as such too. So I'm going to use these 2 properties. So from these 2 properties, I can observe the following. So if we fix T pair, and then what is the row of N corresponding to T? Well, the matrix N is defined in this manner. It is 0 or 1. So if you let B vary over the set of all blocks, then you get the row vector corresponding to the set T. How does the row vector look like? Well, by the property 1, there are exactly 2 blocks, say B1, B2, containing T. So we name them B1, B2. So that means this 1 occurs precisely B is either B1 or B2. So if you let B vary over the set B, then you almost always get 0, except at 2 positions, B1 and B2. So at B1 position and B2 position, remember that these vectors are indexed by the set of blocks. So exactly 2 positions, you get B1, B2. But B1, B2 are known sets. And B1, B2 are distinct blocks. So by the second property, distinct blocks meet in 2 points. And the 2 points must be the same as T, because B1, B2 both contain T. So intersection contain T, but T also has size 2 and intersection has size 2, so they are the same. So once you get so this is the shape of the vector NT. But then it's intuitively clear that the row vectors of N are pairwise distinct. Yeah, let me explain why. So T can be written as intersection of 2 blocks. And suppose that there is another T prime, which gives identical row of N corresponding to T. What does it mean? So that means the row of T and row of T prime have same entry, where entries are indexed by B. We know NTB, this is 1 or 0 according to B is B1 or B2. While NT prime B, this is by definition 1 or 0 according to T prime is contained in B or not. So this occurrence of 1 and 0 coincide. So that means the set B1, B2 is same as the set of B satisfying this property. That is this set. So that in particular implies that B1 is in this set. So B1 contains T prime, and that's same for the B2. So B1 and B2 both contain T prime. So intersection also contains T prime. But the intersection was T. We already know that. So T contains T prime. But T and T prime are both two-element sets. So T is equal to T prime. So what we have shown that if N has a row corresponding to T prime identical to the row of N corresponding to T, then T is equal to T prime. So that shows that N has distinct row vectors. So this example gives the answer to the original question, and it has only 7 blocks. So it is considerably smaller than 21 or even 20. But we already show that the minimum is at least 5 because 21 is smaller than 2 to the power 5. So the minimum has to be one of the 3 numbers, 5, 6, or 7. The answer turns out to be 6, but I will not show the full proof that the answer is 6. If you're interested, you might want to try to prove it. I will give you a hint at the end. So since we have found that the 742 design gives the answer, so the minimum should be at most 7. And I will show that minimum can be reduced to 6. The idea is quite simple. In fact, the idea has been already mentioned in the beginning. That is to omit the very last test. That was to use the same technique to reduce 21 to 20. So let B be the set of blocks of 2742 design. So there are 7 blocks, and fix arbitrary B0. Okay, and remove that block. So we will have only 6 blocks in this set family B prime. So instead of taking this original B, the set of blocks of that design, take B prime consisting of only of 6 blocks and create the matrix N as before. And we claim that even this matrix N has pairwise distinct rows. Why? Well, it is easy to see by if you imagine the matrix in terms of the table of numbers. So originally you have a set of all blocks B. And the trick is to omit the last experiment, which I denote by B0. This is the matrix N for the entire set of blocks. So the column row vectors are indexed by P choose 2. the set of row vectors are partitioned into two parts. First part has 0 in the last column, and the second part has 1 in the last column. 0 means that T corresponding to that row is not contained in B0. And 1 means that T is contained in 1. Both possibility occur. So that's what I divide into two cases. Well, here I have an exact formula, but it's easy to understand what, if you remember how the row vector looks like. If you take a element T, then T is an intersection of, or T is always an intersection of two blocks. And these two blocks, B1, B2, are precisely the one where entry 1 occurs in the row vector corresponding to T. The rest are all there. And then if T is contained in B0, then of course the row vector looks like the same, but we already know that in the last column we have 1. So B0 is one of B1 or B2, because B0 contains that T. So in the second case, we have only 1, 1 except B0, and all the rest are 0. Now we remove the last column. It is clear that the first part and second part consist of different vectors, because in the first part, I have vectors with 2 1s. In the second part, I have vectors of single 1. So we can separate into two cases. And among the first part, the vectors are certainly different, because these vectors essentially come from the original vectors for this set B, and they are already shown to be distinct. The only difference is that this extra 0, which were forgotten. And also, this second case, you can't have same 1 here, because otherwise you would have same vector, same row vector appearing in the original metric sense. That's absurd. So even if you delete the last column to make the number of columns to be 6, still row vectors are distinct. So I claim even in this case, the row vectors are pairwise distinct. So now minimum is down to at most 6. Okay, now the easy counting was that the minimum is at least 5. So we have just two possibilities. Is minimum equal to 5, or minimum is indeed 6? Well, I claim that this minimum is 6. So there cannot be a set family of size 5 meeting the requirement. Well, you might want to use computer to check the all possible set family consists of 5 element sets to see if this is possible or not. Well, it may not be a good idea to do that, because the set family, there are 91 possible subsets or possible collection for tests, because that's each block has size 2, 3, or 4 in a 7-element set. So the number of blocks, the blocks is in one of the 91 element set of 2, 3, or 4 element set. Now you have to choose 5 elements from this set to make a set family, and then see if this 5-element set family could meet the requirement. But 91 choose 5 is in fact quite large. It may be possible if you write a very fast computer program, but I don't recommend that. Certainly, you don't want to create and store the set of all 5-element set of a 91-element set. Unless you have a very large computer, it won't fit in your in the computer memory. So, so if you are interested, try to show the impossibility by hand. Here's a hint. The hint is that you decompose. So suppose you have a 5-element set family and create the matrix N. So this is the matrix N, and you divide the column into 3 parts and row into several parts. Well, here I have only 4 parts, but it could be many parts. There could be many parts. So the columns are divided in this manner. Because this set family B consists of 2-element set or 3-element set or 4-element set. But anyway, the total number is 5. But you don't know how many 2-element set B has. You don't know how many B-element set B has. 3-element set B has. But the total is 5. And the row vectors are also decomposed into smaller parts. The rows are indexed by 2-element sets. And row vector are decomposed according to row sum. This is a 0, 1 vector. So the smallest possible row sum is 0. The next 1 and 2 and so on. So there may be several different parts. And then count the column sum. What is the column sum? Column sum counts if you pick a 2-element set here, then count the total number of 2-element set contained in that 2-element set. Of course, there is only 1 itself. So the column sum is 1. And if you take a 3-element set, how many T are there? Well, 3 choose 2 is 3. So the column sum is 3. And if you take a 4-element set, there are 4 choose 2 elements. 4 choose 2 2-element sets. So the column sum is 4. Okay, so this gives a system of linear equations. You don't know how many vectors here, and you don't know how many vectors here, but you can create a system of linear equations. Okay, that's the hint I have. And that's the end of the lecture.
Okay, thank you very much, Professor Munemasa. So for the audience, if you have any questions, you can ask directly to Professor Munemasa. First, maybe you need to raise your hands, and then you can open your mic and ask the questions directly. Maybe we will wait for a while. I'm sorry.
Prita, can you still hear me?
Yes.
Yeah,
sorry.
I'm running out of battery of my microphone. Oh yeah, that's wireless.
Yes.
So if you can't hear me, then I will try to replace the microphone.
It's okay. I can still listen to your voice.
Good.
Okay, is there any questions? Sorry. Okay, if there is okay, if there is no question, let's
Recording in progress.
sorry, Dr. Rudy, are you still there?
Yes, I am.
I'm sorry, Professor. My child is crying, so maybe Dr. Rudy will replace my place for a while. I'm so sorry.
Everyone, because Bu Prita is quite busy right there. So if you have any question, please raise your hand and you can ask Professor Munemasa directly. Maybe Ijaz, I believe you are quite active in this meeting. Do you have any question regarding the topic?
No question.
Maybe they're preparing or yeah, quite shy. Okay, maybe while we are waiting for the student to ask the question, Pak Pujo, can you help us to take a picture together with Professor Munemasa?
Yes, Mr. Rudy. So I ask every participants to turn on the camera. Make it gallery. We have 4 pages here. Okay, I will take a screenshot. First pages. Okay. And then the second one. Please wait. For the third one. Yeah. And here on the last page. We have 84 participants today. Thank you.
Okay, thank you very much, Pak Pujo, for the help. So, Bu Prita, can you take over again, or let me finish this?
Okay, thank you very much, Dr. Rudy.
You're welcome.
I'm sorry, Professor Munemasa. Now currently my child is crying so loud, so sorry. Okay, thank you very much, Professor Munemasa, for the interesting lecture. Let's give us a virtual applause. Okay, thank you.
Yeah, thank you.
Thank you very much.
For listening.
Let's meet in another event. Thank you, Professor.
Yeah.
Goodbye, everyone. Let's meet
Bye,
at the next lecture tomorrow, everyone. Thank you so much.
Thank you very much, Professor.
Thank you, Professor Munemasa.
Bye-bye.
Arigatou gozaimasu.
Bye.